Okay, this is a relatively short talk about one aspect of water quality that's particularly important, and that is dissolved oxygen. And then I also want to touch on the unique aspects of nitrate and why that's such an important individual contaminant. In the water quality chapter, both of these water quality parameters are covered, uh, dissolved oxygen and nitrate. I want to emphasize them here because they really drive a lot of what's going on with water quality problems. And in the Water 4.0 book, there's quite a bit of discussion about dissolved oxygen and reduced compounds and hydrogen sulfide and the great stink and all that, which that's one of my favorite parts of that book, The Great Stink. So I want to just dig in a little deeper to uh, basic conceptual chemistry of dissolved oxygen and uh, what biological oxygen demand is and sort of how it works. And it all starts with here, this slide we're showing here, photosynthesis. If you remember from gosh knows what coursework, photosynthesis is a plant taking in carbon dioxide and water and energy from the sun and producing, this is a sugar molecule, but you could also just call this CHO. It's just plant material. And it could be thought of as a piece of wood or leaf or any plant tissue, let's say. And the plants, as you know, breathe out oxygen, which is very nice of them to do. So this is combined carbon, hydrogen, oxygen molecule. Like I say, let's think of it as a piece of wood, is stored chemical energy that's produced by plants from photosynthesis. The flip side of this is respiration, and that is taking that yellow box, the stored chemical energy, the sugar, piece of wood, leaf, adding oxygen, consuming oxygen, and producing carbon dioxide and water, and the energy comes back out. Energy in, energy out. Plants trap sun to make energy, trap it in this chemical energy. We take the product, the plant, combine it with oxygen, produce carbon dioxide, water, and we get the energy out. This also could be, and it's the most extreme case, is burning, just taking wood. So fire, if it's hot enough, will consume the oxygen, belching out carbon dioxide, and in that case, the energy is in heat. But in any case, if you're eating a vegetable or whatever, to get energy, you're eating the stored solar energy that the plant traps for you. So that's the basics. Why this is important for water specifically is this oxygen term here. Because when you put organic matter, poo or a leaf or whatever in the water, bacteria will recognize that energy and it will want that stored energy in here to grab. And what it'll do is it will take oxygen that's dissolved in the water and combine it with that and do this reaction. And the problem with that for water quality is that the dissolved oxygen then will be consumed. And I think it's in that chapter. If it's not, I'll have to re-emphasize. Dissolved oxygen doesn't have a great ability to dissolve in water. So typically water coming out of your tap at room temperature has about 6 or 8 parts per million dissolved oxygen. That's not very much. It turns out when the water is very, very cold, it can hold more oxygen, up to a maximum of about 14 parts per million. If you heat it up, it can't hold the oxygen as well, and you get down to 1 or 2 parts per million. So, like if you have a fish tank and the water heats up, your fish will die. The point is, the water is pretty darn sensitive. It doesn't have much dissolved oxygen in it to begin with. So a little bit of this biological material will end up consuming it. And that's, again, discussed quite a bit in the Water 4.0 textbook. Yeah, let me skip over. This is more about respiration. If you've had biology and chemistry, you might want to refresh on this. What I want to talk about here is this chart here. And this is what is touched upon in the book, but I want to get into it a little bit more detail. You start with a molecular energy source at the top. That's like a piece of wood or a leaf. And if there's oxygen available, you go down this pathway, this aerobic pathway, and you end up making carbon dioxide and water. If there's oxygen is depleted, you'll end up going down the anaerobic pathway. And what that is you end up using different electron acceptors, is the term, and end up producing other products. So uh, if you have oxygen and you add a biological oxygen demand, let's say you have a nice oxygenated water coming out of the mountains, it's got 10 parts per million, the water's cold and wonderful, and you throw in a bunch of energy source, you throw in a bunch of biological material, bacteria will love that, and they will use the oxygen as an electron acceptor and produce water. That once that oxygen is depleted, then other bacteria will step in and use nitrate as an electron acceptor to accomplish the same goal. They're all breaking down the biological material, and you'll end up producing nitrite. And after the nitrite is depleted, they'll take iron and make iron. This is what can cause some swampy water to be rust colored. The iron ends up looking like that. Um, Here's where the book touches on these two guys. Hydrogen, this is hydrogen sulfide here, the H2S, and methane, CH4. So after the oxygen is depleted and these other potential electron acceptors are depleted, then you get anaerobic bacteria that will come in and use sulfate. There's probably some sulfate in the water. That's cool. The bacteria will use sulfate to facilitate this reaction of breaking down that organic matter. And when they do that, they produce hydrogen sulfide. That's the rotten egg smell. That's the great stink. The other thing that they can do is find CO2 in the water and use that. And when they use CO2 for an electron acceptor in this reaction, then they produce methane. So I skipped over the hardcore chemistry about the transfer of the electron. Just suffice to say that when you do this reaction, when you take organic matter and you respire it, you're literally transferring electrons from the organic matter. The bacteria are stripping electrons off this thing and shoving them on to an electron acceptor. And when you use oxygen as an electron acceptor, you get carbon dioxide and water. So that's the term. And again, when you run out of oxygen as an electron acceptor, then you go to other electron acceptors and make these other products. So anyway, the reason that a swamp stinks sometimes is that you're out of oxygen as an electron acceptor. Bacteria are working away at the organic matter and they're using sulfate. When they do that, they make stinky hydrogen sulfide gas, or they're using carbon dioxide and they're producing methane. The last note here, and email me or we can chat further if you want to get into the chemistry further. It's a little above and beyond, I think, for this class, but it is fascinating. The last point here, sort of conceptual chemistry, is the reason that the oxygen is used first, and it kind of goes down this line, is that the bacteria get a lot more energy when they use oxygen as an electron acceptor. So if you take some organic matter and get electrons off of that organic matter and put it on oxygen and you'll get a lot of energy. If all these are gone and all you've got is some CO2 left, you're not going to get much energy out of when you take organic matter, shove electrons on carbon dioxide and make methane, which is flammable. You won't get much energy out of that. So that's kind of the nuts and bolts of that. What I want you to be able to do, I have a problem set up where I have like a hypothetical case of a river flowing through development, and various things happen to the river. People add sewage or other biological oxygen demand, and ask you what kind of parameters you might expect to find and why. So I want to switch gears and move into the unique nitrate. There in the salinity paper, there's a little paragraph there called nitrate, the unique salt. And there's so much going on with nitrate now because of agriculture, frankly, mostly. You've probably heard about eutrophication, the problem of having too much nitrate put on the ground in lawns or on fields, having that nitrate flush out into surface water, providing nutrients for algae to bloom. The algae blooms, then it dies, and then the bacteria do their thing and start to decay the algae. And when they do that, they consume the dissolved oxygen, and so you end up with dead water. Um, so this is a lot due to just excess nitrogen. So I want to talk about the nitrogen cycle and leave you with, you've heard about it, the Haber-Bosch process and how that literally has changed the world. So the way I like to start with this is a little bit odd, but what this is a table of the content of plants. If you took a plant and you burned it to, to a crisp and ran it through a chemical machine to tell you what it was made out of, it would look something like this. I'm obviously not going to ask you to memorize this table or something like that. I'm trying to get a point across here that as you go down this table, there's more and more of the plant is made of these things. So you start, there's a little bit of molybdenum, sorry, a little bit of copper, little zinc, manganese, iron, boron, chlorine, sulfur. So these elements plants can pretty easily find in trace levels in soils. These usually aren't going to be the limiting factor for a plant to grow. So again, the logic here, this is the composition of what a plant's made out of. So if you wanted to grow a plant, you'd think you'd have those things handy. Now you get down to here: phosphorus, magnesium, calcium, potassium, and nitrate. Calcium and magnesium are very fundamental elements of the Earth's crust. Again, you'll probably find plenty of that in the soil. And that leaves the big three: phosphorus, potassium, and nitrogen. Nitrogen, potassium, phosphorus, NPK. So when you go, the chemical symbol for potassium is K. So when you go to Home Depot or whatever and get some fertilizer, they will give you ratios of NPK, nitrogen, potassium. This is what the plants want that is not available in the soil at enough, and it limits their growth. And here we're going to focus on nitrogen because there's a really cool video by Frank Green that I have. I really want you to watch. It's kind of fun. But there was, basically in a nutshell, in the mid 1800s, a thought that we're going to, as a species, start facing mass starvation because our agriculture yields were sort of leveling off, and that's going to make the population level off at some number of billions of people. And the thought was there's going to be mass starvation. One of the innovations, whether you like it or not, that occurred was the idea to take that nitrogen is really one of the biggest limiting sources to growing food. And agriculture was looking all over the world for sources of nitrogen. You saw the night soil application of finding nitrogen in human waste, certainly limitations there. For a while, folks were harvesting bat and bird guano off of islands that is loaded in nitrogen. Very nice, but obviously there's not only so much of that you can do. It turns out that our atmosphere is 80% nitrogen gas, N2. And so, gosh, if there was a way to get that nitrogen out of the air and get it into a fertilizer, wouldn't that be interesting. And there was an individual who really was instrumental in inventing a process to do that. And that process is credited, again, whether you think it's a good idea or not, with about doubling the population on the planet. So it's a very fascinating story. But anyway, that's why nitrogen is such a focus for water quality in California and a lot of other places. Here's something that I do want you to know about. I would want you to be able to basically fill in the gaps here of how nitrogen is cycled naturally on the planet. So this is the natural cycle of nitrogen that plants can fix nitrogen from the atmosphere. The legumes can to some extent. Um, and so that's one way to get nitrogen gas, this N2, in the atmosphere into a form that plants can use through certain bacteria and fungus in a rhizosphere of roots of legumes. Nitrogen fixing bacteria. Uh, you ultimately the stages are to do that and to get the nitrogen into this ammonium form, NH4. That is then reduced to nitrate, and nitrates can this NO3. That's the nitrate that can really be used by plants. And you might have heard of this denitrifying step that takes nitrate and turns it back to nitrogen gas in the atmosphere. So this is the natural cycle, and the thing that's really, really interesting is, again, we human beings can be pretty inventive. We found a way to take this N2 in the atmosphere and directly turn it into NO3. And by doing that, really, really up the production of plant matter on the planet. But of course, as you can imagine, that's come with some cost. The other diagrams here are just more of the same thing. It's just, if you like the artwork more, really, I think these are helpful to visualize, but I'd like you to be able to, understand basics of how nitrogen gas is naturally fixed and moves through this system. I don't know quite. It looks like somebody's growing some cannabis here with a rabbit. Whatever you like as far as the artwork goes. Here's another way of a little bit more chemically intense way to look at the cycle. And okay, so I'll leave it with that, and just again, check out the Hank Green YouTube video on the Haber process. Understand the natural nitrogen cycle, and understand the concept of, photosynthesis and respiration and aerobic respiration versus anaerobic respiration and the byproducts that can be